Swayam Prabha. Digital India. Educated India.
Having done these examples, now I am in a position to also explain what we saw in the demonstrations. Recall the demonstration where I had a bicycle wheel which was rotating. Let us say it was rotating like this, and when this rotating wheel was pivoted at this point, it also started going around like this, what is known as precession. Let us have a look at that. What I showed you was, here was a bicycle wheel which I rotated like this, and when I put it here, it started going around like this. When I gave the rotation the other way, it rotated the other way. Let us try to understand this. Our observation is that it is rotating. When I have this bicycle wheel and it is turning like this, you can see that it has an angular momentum in this direction. Let me call it angular momentum due to the spin. Since it is pivoted here and it is being pulled down like this, it is not moving up and down, although very slight movement is there, that we will explain later. We can, for the time being, assume that there is a normal reaction N which is equal to mg, so that center of mass does not move up and down. What this N and mg together they do is provide a torque or a couple which is equal to, suppose this length is L and this angle is theta from the vertical, then the torque provided by them is mg L sin theta. And what about the direction? The way I have shown it right now, the bicycle wheel is like this. This is mg, this is N. So the way I have shown it, the torque is going into the plane of the screen. So this Ls must change. And how does it change? It has to change direction. It has to change into, the delta L has to be into the screen. For the time being, we will assume that the spin is so large that this rotation, precession that I am talking about, does not really affect its spin angular momentum much, although in principle you should be taking components of this rotation also to describe angular momentum, but right now we will ignore it. Then you see that Ls has to change going into the plane. If I go back to this demonstration, this is the direction of angular momentum, and when there is a torque applied like this, the angular momentum has to go like this. If the angular momentum has to go like this, the body rotates, and this is precisely what we see. Let us do that now. Let us give it an angular momentum in this direction, therefore the wheel has to rotate like this, and when I leave it, it rotates like this. If I give it the rotation the other way, if I rotate it like this, then the angular momentum would be in this direction. The torque m cross g is this way, so the angular momentum has to rotate in this direction, and therefore it should rotate the other way. Let us do that. And you see it goes the other way. We can also calculate the rate of this rotation. So this torque must be equal to the magnitude of rate of rotation. Suppose this rotation is at rate omega, that means the angular frequency about this vertical axis is this way, then this should be equal to omega times LH, which is dl dt. Why? Because the vertical component of L does not change, the horizontal component sweeps, as we saw earlier. Let me make a nice picture again. This is the wheel, this is L spin, this is the vertical component which does not change. The horizontal component, if this angle is theta, is going to be Ls sine theta. There is an mg acting downwards, there is an n acting upward. So tau should be equal to dl dt. We have already made sure of the directions by demonstration as well as by working out here. So tau magnitude is going to be equal to capital omega, which is the rate of precession, times L horizontal, and this we calculated to be mg L sine theta, and this should be equal to omega L spin sine theta. Sine theta cancels, and therefore you get L spin is equal to mgl divided by omega L spin equals this, and therefore omega equals mgl divided by L spin, and that's your answer. No matter what angle it is at, the precession frequency is the same. If very high spin rate is there, omega is going to be very small, and therefore I ignored any effects due to capital omega, which is generally known as gyroscopic approximation. The second demonstration that I am going to explain now is going to be this gyroscope, and what we had noticed in this gyroscope was that there are three independently rotating objects. One is this frame which can rotate about this horizontal axis, one is this frame which can rotate about the vertical axis, which is mounted on this frame, outer frame, and there is this wheel. And what we noticed was, suppose I give it a spin and then rotate the outer frame, the spin tends to align with the spin direction of the outer frame. Let us see it again. I will give it a rotation, and as I rotate this, it tends to align with this. Let us try to understand this in terms of angular momentum. What I have is, I will try to make a picture. There is an outer frame like this, which can rotate about the horizontal axis. In this outer frame, there is an inner frame. Let me make it like this, which can rotate about this vertical axis, and in this inner frame I have a wheel which is like this. Let me look at it from a different view. The outer frame is like this, and let this frame, inner frame, be in the position like this, you see this way, and then the wheel is mounted like this. Suppose the wheel is given a rotation, a spin by omega, and we rotate after that this with omega. What we see is this whole inner assembly rotates in such a manner so that the spin wheel aligns with this spin. You see that again. Let us understand why that happens. When it is rotating like this, you will see that this has an angular momentum going into the plane. As soon as I give the outer frame a rotation, this angular momentum would tend to go down. So as soon as I rotate it like this angular momentum develops a delta L going down. However, assuming everything is frictionless, there is no torque on the system taking it, which can change angular momentum going down. If there is no torque, there should really be no change in L as far as the vertical direction is concerned. So what does this frame do? It rotates in such a manner so that it develops a corresponding delta L in this direction, in order that net change in the angular momentum is 0, and that means it will tend to rotate like this. This frame would come out here and go in here, so that it develops an angular momentum in this direction, and that is why this whole thing aligns with omega. Having qualitatively understood this, That is, if we have these frames, this can rotate freely about this can rotate freely about this, and this can rotate like this. Why this spin aligns with the outer spin? Let us try to make it quantitative. To make it quantitative, let me make this outer frame, let me make the inner frame, and let this wheel, inner wheel, be such that its axis is making an angle theta with this direction, making an angle theta coming out of the plane of the screen. If this angular momentum is Ls, that is the angular momentum of the inner wheel, this wheel spin is Ls, its horizontal component coming out of the screen is going to be Ls sin theta, Ls horizontal. I am assuming it is making an angle with this. So what I am assuming is, here is the axis and this fellow is making an angle like this with this axis. So this angle, so therefore the component in this direction is going to be Ls sin theta, and along the axis is going to be Ln cosine theta. Ls sin theta, if this theta is very small, is going to be roughly equal to Ls theta. Now when I give the outer frame a rotation, you see this component changes, this component develops a delta L in this direction. And how much is that delta L? You can see this is horizontal, is going to go down, is going to be outer omega times delta t times this component itself. So delta L is going to be equal to Ls theta times omega delta t, this way. However, there is no torque in this direction, and therefore delta L in this direction should be 0. What would happen? This frame would rotate in this manner so that it develops a delta L in this direction. So it will gain an acceleration or a velocity in this direction so that this delta L gets 0, and that gain should be delta L is equal to I, whatever I is about this axis, theta double dot, because it is going to go that way, it will change theta, times delta t. This is I omega in the direction opposite to theta, and therefore I should have I theta double dot delta t is equal to minus L spin theta omega delta t. This cancels and I get an equation for theta. Theta double dot is plus Ls omega over I theta is equal to 0. This is like a harmonic oscillator equation, and therefore if it is spinning and I make an omega, it should oscillate about that omega axis. Let us see that. Here is a small angle. Let me give it a spin like this, and let us rotate the outer frame, and you see this is oscillating.